Welcome to the deep dive. Today, we are jumping right into a really um, fascinating debate that's stirring things up in AI research. It's all about how smart these large language models, LLMs, and maybe the more specialized large reasoning models, LRMs, how smart they really are, especially when you give them, really complex problems to solve.
Yeah, it's a huge question right now, isn't it? Are they actually reasoning, thinking things through, or is it just incredibly sophisticated pattern matching?
Exactly, and we've got some great source material for this dive. There's a recent 9 to 5 Mac piece looking at a new research paper. In this new paper, it goes right up against an earlier study, a big one, widely cited, that came out of Apple.
So you've got one group saying, look, here are the limits, and then another group coming back saying, hang on, maybe you didn't test those limits quite right.
That's basically it. So our mission today, just for you listening, is to kind of unpack this whole thing. Cut through the jargon. We want to understand the arguments on both sides, what's really going on with how we test these AIs, and maybe figure out what it tells us about AI capabilities. And, maybe even more critical, how we should be measuring them. Get to those surprising insights.
Okay, sounds good. Let's dig in.
Right. So let's start with that first paper, the one from Apple researchers that kind of kicked this off. It was called The Illusion of Thinking. Pretty provocative title. And the conclusion definitely grabbed headlines.
Yes, it certainly did. The main finding, what they reported, was that even the most advanced models, these LRMs, they just hit a wall. They talked about an accuracy collapse. Basically, the models failed completely when the puzzles got too complex.
Failed completely, like zero success. What kind of puzzles are we talking about? Yeah, near zero accuracy in some cases. They used classic logic puzzles, things like the Tower of Hanoi moving disks between pegs, and also river crossing problems, getting people or things across a river with constraints on the boat size.
Right.
And the Apple paper specifically said for Tower of Hanoi, once you got to 8 or more disks, performance just plummeted.
So the message from Apple was essentially, we push these models, and look, they break. They can't handle complex multi-step planning. It looks like thinking, but it's just an illusion because it falls apart.
That was the strong implication, yes.
Yeah.
That there's a fundamental reasoning limit there, especially for tasks needing long chains of logical steps.
Okay. But then comes this counter argument, the new paper, and I love this title, The Illusion of Thinking. This one's from Lawsen at Open Philanthropy. And interestingly, it lists Anthropic's Claude Opus model as a co-author. That's pretty cool. So what's their main point? Well, this is where it gets really interesting. They don't necessarily dispute that the model struggled on Apple's specific tests. Instead, they argue the reason for the struggle wasn't a fundamental lack of reasoning ability. It was, they claim, flaws in the test design itself, how the experiments were set up and evaluated.
Ah, okay. So it's not the AI can't think, it's more like your test didn't let the AI show its thinking. Is that the idea?
That's the core of it, yeah. Less an illusion of thinking inside the AI and more an illusion of evaluation caused by the test setup. The test might have been the real problem, not the AI's core capability.
Okay, now I'm hooked. This is fascinating. Let's get into the details. What specific problems did Lawson's paper find with Apple's evaluation?
Well, one of the biggest critiques, maybe the most straightforward one, has to do with token limits. Apple's tests, especially for the harder puzzles, required the models to output really, really long sequences of moves to count as a correct solution.
You mean like for complex Tower of Hanoi, it had to list out thousands and thousands of individual steps perfectly?
Exactly. Thousands, potentially tens of thousands or more. And Lawson's paper points out that the complexity level where Apple reported this collapse in performance, that point often lined up perfectly with the models hitting their maximum output token limits. The hard cap on how much text they can physically generate in one go. Like 64,000 tokens or maybe 100,000?
Wait, so the model might have actually known the pattern, known the next steps, but it literally couldn't type anymore. It ran out of space.
That's the argument. And it's a strong one. They even found examples in the model outputs where the AI said it was starving because of length limits. The source mentioned one model outputting something like, the pattern continues, but I'll stop here to save tokens.
Wow. Okay, that's pretty damning for the original test interpretation, isn't it? It's not saying, I'm confused. It's saying, I have to stop because you capped my output.
Precisely. So the argument is that test wasn't really measuring reasoning or logic in that instance. It was measuring the ability to generate an incredibly long, perfect list within a fixed output size. And if you can't do that, it looks like a reasoning failure under Apple scoring, but maybe it's just a practical limitation of the output format.
Okay, that's a huge point. What was the second major critique? You said this one was Surprising.
Yeah, this one is quite something. They call it the impossible puzzle problem. Lawson's paper presents evidence that some of the river crossing puzzle instances included in Apple's tests were actually mathematically impossible to solve.
Impossible. How does that happen? You mean the test included problems that literally have no solution?
That's what they claim. They point to specific configurations, like trying to move 6 or more pairs of things across a river with only a 3-capacity boat. Apparently, it's known in puzzle theory that those specific setups they don't work. There's no valid sequence of moves.
So Apple's automated test was expecting the AI to find a solution where none existed.
Exactly. And because the automated system was just looking for a correct sequence of moves, when the model didn't provide one, because it couldn't, or perhaps even correctly inferred it was impossible, it got marked as a failure.
That just seems fundamentally flawed.
Right. Lawson's point is critical here. The models weren't failing to reason. They were, in a sense, being penalized for correctly identifying or at least behaving consistently with an impossible task. It's like, giving an equation with no real solution to a calculator and marking the calculator as failed because it didn't give you a number.
Yeah, or like that SAT analogy in the source, marking a solver wrong because it correctly said an unsolvable logic puzzle was unsolvable. You're testing the wrong thing.
Precisely. It points to a potential major issue in the test data itself, which would automatically make models look like they're failing, regardless of their actual reasoning power.
Okay, impossible puzzles.
Yeah.
Token limits.
Yeah.
What was the third main critique of how Apple evaluated the models?
The third point kind of ties the first two together. It's about the rigidity of the automated evaluation system Apple used. Basically, their scripts judged success only if the model produced a perfect, complete, step-by-step list of moves for the entire puzzle.
So one wrong move, one missed step, even in a sequence that's thousands of steps long, that meant the whole thing was scored as 0, a complete failure.
That's how it seems to have worked, yes, an all-or-nothing approach. And that kind of scoring, Lawson argues, is problematic because it can't tell the difference between different kinds of failure. It doesn't distinguish between a model that genuinely gets stuck and doesn't know the next logical step, which would be a reasoning failure, and a model that stops because it hit the token limit. Or maybe recognized the task was impossible, or even just made one tiny mistake in an otherwise perfect 1,000-step sequence.
And there was a statistical point tied to this too, right? About long outputs.
Yes, they bring up the idea of statistical inevitability of errors. Think about it. Even if a model is incredibly accurate, say 99.9% accurate for every single token it generates, the chance of it producing a perfect sequence with 0 errors becomes vanishingly small as the required sequence gets really long. For a sequence needing, say, 10,000 tokens, that 0.999 accuracy per token still means the probability of getting the entire sequence perfect is tiny. Less than 0.005%, according to their calculation.
Okay, yeah, that makes intuitive sense. The longer the chain, the more chances for one weak link, even if all the links are individually very strong.
Right. So under that strict all-or-nothing scoring Apple used, hitting token limits or just making one tiny slip-up over thousands of steps looks exactly the same as a complete inability to reason about the problem, even if the model fundamentally understood the logic and got 99% of it right.
So if these critiques hold up token limits, impossible puzzles, rigid scoring, suggest the models might actually be better at reasoning than Apple's test showed. How did Lawson's team try to demonstrate that potential capability?
They took a different approach to testing. Instead of demanding that huge, exhaustive list of moves for a really complex Tower of Hanoi problem like N14 disks, which is way past where Apple saw failure and involves hundreds of thousands of moves, they asked the models to do something else entirely.
What do they ask for?
They asked the models to generate code, specifically a recursive function in the Lua programming language. And this function, when you run it, would print out the correct sequence of moves for the N15 Tower of Hanoi puzzle.
Ah, okay, so not give me the massive answer, but give me the recipe to generate the massive answer. That's clever.
Exactly. It tests whether the model understands the underlying algorithm, the recursive logic of the puzzle, and can express that logic correctly in code.
And what happened? How did the models do on that task?
The results were pretty striking. The models they tested, they mentioned Claude, Gemini, and OpenAI models, were actually very successful at generating the correct code for N15. Remember, this is a complexity level where Apple's method showed basically 0 success.
And generating the code itself?
Oh.
That takes fewer tokens, I assume.
Way fewer. under 5,000 tokens to generate the correct Lua function, compared to the hundreds of thousands potentially needed to list out all the moves for N15. So it strongly suggests the models could graph the logic and provide a working solution method, but they were being tripped up by the demand for that impossibly long, perfect output sequence in the original tests.
So the takeaway is change the test format, make it about showing the understanding of the algorithm rather than just perfectly executing a massive output, and suddenly you see reasoning capabilities that seem to be missing before.
That's the core argument, yes. It's about separating the model's understanding of the problem's logic from its ability to perform perfect, exhaustive enumeration under strict and perhaps unrealistic output constraints, which maybe current models just aren't built for, or at least not reliably.
Okay, let's step back for a second. This technical back and forth is fascinating, but what does it mean for you listening right now? Why does this debate about test design matter?
Well, it matters a lot because that original Apple paper got so much attention. It was widely seen and reported as proof that even the best AIs have these hard limits on their reasoning. That narrative feeds into how everyone, policymakers, businesses, the public, thinks about what AI can realistically do and how close we are to, more general intelligence.
And if Lawson's critique is valid, then that widely cited evidence might be, well, not wrong exactly, but maybe misinterpreted based on a potentially flawed test.
Exactly. The rebuttal suggests the reality is more nuanced. Maybe the models do struggle, but the struggle wasn't necessarily a fundamental reasoning failure. It could have been them hitting practical limits like token caps or dealing with impossible tasks or being judged by an overly harsh all-or-nothing standard.
Yeah, if we connect this to the bigger picture, like you said earlier, it really underscores how tricky it is to design tests that actually measure what we think we're measuring with AI. Are we testing reasoning? Or are we testing perfect recall?
Right.
Or the ability to follow output formatting rules? It gets complicated fast.
It's a critical distinction. Are we seeing the limits of the AI's intelligence or the limits of our current methods for testing that intelligence? Now, Lawson's paper isn't saying the models are perfect reasoning machines. They acknowledge there are still real challenges like true algorithmic generalization applying logic learned in one context to a totally new one.
But it does push back hard on the idea that there's just a simple reasoning collapse when planning problems get complex.
Definitely. It suggests the picture is more complex. Model capabilities might be stronger than we thought, but they're sensitive to how we ask the question and how we measure the answer.
So based on all these critiques, what does Lawson's paper suggest for the future? How should researchers be evaluating AI reasoning better?
They offer some clear recommendations, drawing right from their findings. First, design your tests specifically to separate reasoning ability from those practical constraints, like token limits. Don't set up a situation where hitting an output cap looks like a failure to think.
Makes sense?
Second, and this seems obvious but apparently insane, check your puzzles. Make sure the problems you're giving the AI are actually solvable before you score the AI on solving them.
Right. Don't penalize it for an impossible task.
Third, think harder about complexity. Don't just measure complexity by the number of steps in the solution. Measure it by the actual computational difficulty, how much search is needed, what's the logical structure.
Like the Tower of Hanoi versus river crossing example.
Exactly. Tower of Hanoi has tons of steps, but a simple algorithm. Computationally, it's relatively easy to describe. River crossing might have fewer steps, but needs much more complex search. It's computationally harder, related to NP-hard problems. That difference matters more than just the solution length. Understanding that might explain model performance better. And finally, be more flexible in how you let the model show its solution. Don't just demand a perfect, exhaustive list of moves. Consider other ways it could demonstrate understanding, like generating code, explaining the strategy in words, or describing the core algorithm. Those might be better probes of reasoning, separate from pure enumeration skill.
Okay, that all sounds like a much more nuanced way to approach evaluation.
Yeah, this whole deep dive, I think, really highlights that understanding AI isn't just about building bigger models and seeing what tasks they can do. It's also crucially about scrutinizing how we test them and interpret those results. There's that great concluding line from the critique paper.
Right. The question isn't whether LRMs can reason, but whether our evaluations can distinguish reasoning from typing.
That really nails it, doesn't it? It puts the onus back on the researchers, on us, to design better tests. Are we actually measuring intelligence, or are we just measuring the model's ability to generate very long strings of text perfectly, which might be an entirely different skill?
So here's a final thought for you to chew on as you hear about the latest AI breakthroughs or limitations. Could the way we're testing AI right now, in all sorts of contexts, be accidentally hiding some of its real capabilities? Are we sometimes mistaking the limitations of our tests for limitations of the AI itself? What happens when we change the test? Ask the question differently. Something to keep in mind as you navigate all the claims about what AI can and cannot.